So after preparing your data through that rank, order distribution, range, simple frequency distribution and group frequency distribution, of course there are other ways of preparing your data as well, but after preparing your data you need to work out how you want to present your data. So you'll often present your data originally in table format. So here you can see you've got, in figure 9, you've got a table full of the raw data of static sprint scores and standing vertical jump scores of gymnasts. You can see here that you've got all of the data for all of the participants, and then on the right hand side you can see that there's an overview in figure 10, so it's kind of like a summary table of the participants' scores, and that's actually included the mean, standard deviation, median, maximum and minimum. So the summary table has included the relevant information. This doesn't necessarily mean that you discard the raw data table. You might put that table in an appendix at the end of your research project, just so that you can refer back to that original raw data. But in reference to putting your data into tables, it generally just allows a more aesthetic and more visual way of looking at your data that you've achieved from your research or from your tests. So obviously the table format is columns and rows, so you're able to look across in columns or in rows and look and refine your view, I suppose, to that column or to that row, making things a bit more easier to read. Generally you'd want to use the same decimal place, so you can see here I've generally done it to 2 decimal places. No more than that, just makes it a bit more easy to read, and then makes it visually more pleasing. You don't want a long line of numbers, makes it more difficult to compare numbers and figures. You want to have the units displayed so that you know what measurement you've used. So here you can obviously see that I've used seconds and centimetres displayed in the table. You want to title your table so that you know what the table is about, whether it's relevant or not. You want to title each category, so obviously I've put participants, static sprints, standing vertical jump in figure 9 you can see, and obviously in figure 10 you can see I've put mean, standard deviation, median, max and minimum. You want to have the figure labels, so sometimes you'd have it displayed as figure 9, figure 10 or whatever, and sometimes you'd have it displayed separately. So for example, graphs might be figure blah 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 and tables might be table 1, 2, 3, so on, just to differentiate, but it's dependent on the researcher really. But the point of it is just to kind of be able to reference back to things quite easily and just reference back to figure 9 rather than having to explain the whole table over again. And yeah, like I said before, you might perhaps want to put a larger table, more detailed table in the appendix and have a more refined summary table as your main content in the research. In general though, in terms of presenting data, not just in tables, but the data is now in a format that is easy to read, meaning the presentation of data will be easier. So quantitative data will usually be displayed in graphs or diagrams for ease of viewing. This includes Venn diagrams, pie charts, histograms, line graphs and scatterplot graphs. The presentation of data in this format means that readers can easily distinguish different data and similar data. The choice of diagram for presenting data will be dependent on the relationships you wish to display or differences you wish to display. For example, a pie chart will show the direct differences in categories, whereas Venn diagrams show differences and similarities. Each diagram will be specific to the way you wish to present your data. Moving on then, we look at the different types of graphs and diagrams that you can use in quantitative data analysis. So graphs basically allow you to visually depict data and trends in data. So with graphs, you want a scientific title, which usually will include the independent variable and dependent variable. You also want your axes to be labelled, so your x and y axes both must be labelled, so you know what your values along the x and y axes actually representing. You want regular intervals really, so you want the same intervals. So for example, in figure 11 you can see for the measurement you're going up in fives, and participants is obviously going up in ones. Like the tables, you want the unit of measurement to be shown as well. Potentially, sometimes you'd use a line of best fit depending on what graph you're using. But yeah, if we move on to the specifics then, obviously presented on the screen now is the line graph. So line graphs basically show a comparison between two different things. So you can see in figure 11 there's a comparison between bicep and tricep measurements from Skinfold caliper. This is to establish the difference between those two measurements. You're comparing the red line to the blue line. And you can see the blue line represents the bicep measurement and the red line represents the tricep measurement. The difference in coloured lines is obviously just to make it a bit easier for you to read, a bit easier visually to distinguish the difference between the two lines. If they were a similar colour, it'd be a bit more difficult to read. So that's obviously another thing you need to take into account when making your graphs. Again, you have that figure label below just to be able to reference back to it. You've got the title at the top, labelled axes, regular intervals, unit of measurement, and so on. You've got to keep all those key factors in there for it to just be easier to read, I suppose. On the right hand side you can see figure 12. This is the exact same table, but instead you've included standard deviation bars. Now I'll go on to explain standard deviation in a bit more detail later on. But to sum it up, if there's no overlap on the standard deviation bars, that means that there's a significant difference between the two sets of data presented. Obviously, if there is an overlap, then it's less likely to be a statistically significant difference. But again, I'll go into more detail about what standard deviation is later on. So in figure 13 you can see that there is a scatter graph presented. Now scatter plot graphs basically show correlation. So this might be a positive or a negative correlation, and they also show the strength of that correlation, so whether it's a strong correlation or negative or weak correlation, sorry. So it presents a relationship. It doesn't present a cause, which may be a fault of the graph. Doesn't explain why there's a positive or negative correlation. but it does show that initial relationship in terms of correlation. So in figure 13 you can see that you're looking at the correlation between flying sprint time and static sprint time. Now again, in terms of presentation of the graph, you've got the labelled axes, you've got the regular intervals, you've got the title with the units of measurement, and the figure 13 and description at the bottom. So with a scatterplot graph, the points, so the blue dots in this case, are representing people or participants in this case. So each individual dot is representing one person's scores. So if you were to go along the y-axis and along the x-axis, that would match up to one dot. You'd have two different values, one for flying sprint time, one for static sprint time, but for one dot. So in terms of whether it's a positive or negative correlation, if the data points make a straight line going from the origin out to a high x and high y value, then it's said to have a positive correlation. Of course, if the line goes from a high value on the x-axis down to a low value on the y-axis, the variables have a negative correlation. There's a statistical side to this as well, so it's not just that presentation of whether it's a straight line vertically, diagonally, or whatnot. You also want to see the strength of the correlation. So a perfect positive correlation is given the value of 1, where a perfect negative correlation is given the value of -1. Now, if there is absolutely no correlation at all, the value is given 0. So a weak positive correlation might be something like 0.21, whereas a strong positive correlation might be something like 0.75. Obviously, a weak negative correlation would be something like -0.21, and so on. The overall idea of a scatterplot graph is basically just to present the relationship and correlation between those values, those two different data sets. So in this case, sprint time, static sprint time, and flying sprint time. Bar graphs show the categorical data. So they show trends in data based on categories. So you can see a really basic version here in figure 14. So this is a bar graph showing the difference between skin fold caliper measurements of bicep in comparison to tricep. So similar to data previously used based on those gymnasts again. So you can see the categories here obviously are bicep measurement and tricep measurement. So you've got the measurement in millimeters, skin fold caliper from 0 to 20, and you've got the participants 1 to so on up to 14. Again, you've got the axis labels, and you've got the title at the top and the figure title at the bottom. So to sum this graph up, it's basically summarizing data into categories so that you can compare the difference between the two categories. So the different coloured bars are shown next to each other, so you can easily distinguish which bar is higher, therefore meaning a higher score, of course. Each participant has a bicep measurement and tricep measurement, and the bar graph plainly shows the difference between the two measurements. You might find trends from this, so you might find that all of the tricep measurements are higher than the bicep, just allows you to show the trends in difference between the categories.